So imagine we lived in our two-dimensional world. So yeah. And we have a heater and a window. So here is the heater, and here is the window. Okay, so the heater is creating heat, right? And the window is cold. That's where the heat is gradually going to diffuse out of. But the heater is on, it's continuing producing heat, right? And then that heat is going to go over, diffuse slowly over that direction, yeah? And if we lived in this world, I mean, this could be our classroom. We could be like sitting in here in the real world, if post-pandemic, pre-pandemic, right? And we'd be like sitting around, moving around. And we also have the heat of our bodies. We're moving the air around, right? Yeah. But if we just stopped, if we were just completely still, then nothing else would be affecting the situation except the heat equation. Yeah. So whatever heat there might have been around here because we brought it in or we're moving around, shifting the air around, it will gradually diffuse towards the steady state, because this is an equation that evolves with respect to time. Right? So if you imagine us sitting in here in the classroom and keeping completely still for whatever, 5 hours, yeah? Then the heat around the room will be fairly close to constant, right? It's coming out from the heater and it's diffusing out towards the window. Yeah? And if we waited an infinite length of time, it would actually be completely constant because nothing would be changing. Yeah? So that would mean that this part would be 0 because the heat is not actually changing with respect to time. So it's different at different points in the room, yeah? But it's not changing with respect to time because we've reached a steady state. Yeah? So letting t go to infinity, we reach a steady state. Where the heat is not changing at any point in the room with respect to time. So at different points in the room, it's different temperatures, obviously, but it's not actually changing with respect to time. And then so we just have that the heat, the steady state of the heat distribution satisfies the Laplacian. Yeah? Satisfies the Laplacian. Yeah? So this is like hot and the heat is diffusing outwards like this. So imagine U is like a large value around this thing here. Yeah? And the window is cold. So we have a function which is high and then decreases towards this. Yeah? That's what we expect as we let time go to infinity. Yeah? Yeah? And at that steady state, we would expect the thing to do this as smoothly as possible, right? Nature is parsimonious. It will, as smoothly as possible, diffuse the heat from the hot to the cold, yeah? And there will be as little oscillation, as little perturbations as possible, right? The perturbations will be smoothed away as we just let this heat profile reach its steady state, yeah? Which makes it reasonable, makes it believable for us that the more spaced out these things are, right, the bigger R we can put around here, yeah, the smaller the higher derivatives will be, the first, the second, the third, right? Yeah? Yeah? So that is a reason why we would expect things that satisfy the Laplacian to have, if you believe that this is a good representation of the steady state of the heat equation, this is a reason why you might expect this to be true, that we have this estimate that if we take the kth order derivative, then it is less than k factorial, the supremum around the boundary of the ball of radius r of the function itself divided by, in this case, r to the k, like this. Yeah? That might seem believable. And what's also true is that functions that satisfy Laplacian have the mean value property. Also, if U is harmonic, then if we take some point, then this is the same as the average around the boundary of the ball of the function, and I'm going to write h1 of c. So we talked about this when we talked about the meaning of Cauchy integral formula. This is just a one-dimensional integral around the curve divided by the length of the ball, right? So if we had a parameterization, so if z of t, which is equal to, I should maybe write, since I'm carefully doing x and y, let's write x0, y0. If we had x of t is x0, y0 plus r of cosine of t, sine of t, that's a parameterization around this curve, right? So from your knowledge of multivariable calculus, this thing is just the integral like this of 1 over 2 pi times r of u of z of t, absolute value of z prime of t, dt. That's what you've learned from multivariable calculus, and we talked about this briefly at one point as well. Yeah? So that's what this means, and I write h1 because later you'll learn that the correct way to integrate one-dimensional curves or over one-dimensional curves is with something called Hausdorff one measure. So just to get you used to this notation, just because I'm used to writing this properly, I put it this. But this is how you should think about this, just having learned multivariable calculus. Because when you have a smooth curve, however you integrate it with Hausdorff measure or this way with the parameterization, it turns out to be exactly the same. Okay, back to this. So we have, this is true for something that solves Laplace's equation, something that's harmonic. And that's a simple calculation, but again, from the idea or from the model of the, or from thinking about solutions of Laplace's equation being steady state of the heat equation, this seems reasonable because look, if we are here, right, and we have the heat is flowing across like this, then at some points around the boundary here of the, or some points around the boundary of the ball, we're going to have the hotter, right? And at some points over here, we're going to have the colder, yeah? And it seems kind of reasonable that the thing in the center will be some kind of an average of what we have around the outside. Yeah? In fact, however you situate your heaters and your windows, however you draw the ball, you'll always see that in the center of the ball, it'll be some kind of an average of what's happening, yeah, as the heat diffuses across. But what is remarkable and kind of fascinating is that it's absolutely an exact average. So that means if you were in your room and you took a soccer ball and then you stuck a bunch of heat sensors around the outside and then you just recorded the heat distribution around the soccer ball as you leave your room to approach the steady state of the heat distribution, and then you integrated over these recordings divided by the surface area of the soccer ball, you would find exactly the area, exactly the heat in the center of the soccer ball, yeah? For any size soccer ball. Yeah? So this is an example of math forcing the universe to be in particular ways, particularly symmetrical ways. If you talk with a physicist, they might say, well, that's a consequence of the heat equation. But as a mathematician, I would say, no, this is a consequence of the fact that if you have the heat equation in a steady state and it satisfies Laplacian, and it's a mathematical theorem that something satisfies Laplacian, satisfies the mean value property. Yeah? So this thing, the fact that you have a harmonic function satisfies the mean value property, essentially reduces down to the divergence theorem, which is just a generalization of the fundamental theorem of calculus. So these mathematical laws imply something about the real world that you probably wouldn't expect. You wouldn't expect exact symmetry, exactly that averaging over the surface of a ball, of the boundary of the ball, would give you the exact temperature in the center, but that's a true thing because the math forces it to be that way. The math forces that thing to be true. It is just a little toy example, but it's an example that there are examples everywhere in nature, in the world, where things are of particular structure because there is an underlying mathematical law forcing them to be this way. If you look around and you look at the planets and see perfect spheres, there's a mathematical reason why. So maths is this underlying order forcing the universe to be in particular ways. And we don't really get much, there's not widely understood. People understand that physical laws force the universe to be in particular ways, but underneath these laws are mathematical laws forcing an even more fundamental structure to be there. And if you're aware of it, you see it all the time. And if you're not, then you just don't notice it. Anyway, that's an example. So given this thing, we can sort of believe this mean value property. And as we learned, Cauchy integral formula, in the case where we take the value at the center of the ball, just reduces down to the mean value property. Right? Yeah. So we've proved Cauchy integral formula, but from this kind of model or this reduction to this physical situation, we can kind of believe it, at least from the case when the value is taken to be at the center of the ball. Yeah? One of the homework exercises I'll give you in your next homework, not this one coming up on Saturday, but the following one, is to do the reverse. So to go from the mean value property for solutions of Laplace's equation, harmonic functions, and prove Cauchy integral formula. And it's straightforward to do that in the case where you just stick the value directly in the center of the circle, because you just reverse the implications I did. Everything was just an equality. It's trivial. But to do it in general is also possible, and a hint is to use the keyhole contour. So it's actually the fact that these things are equivalent if you have enough integrability to actually deduce the Laplacian. So we need Cauchy integral formula to prove the existence of higher derivatives of holomorphic functions. But if you have a holomorphic function, which just by some reason you're given that it has a second derivative, then you can deduce Cauchy integral formula from the mean value property. And that's going to be something you're going to see. And this is an example of what I've been saying, that a lot of these complex analysis theorems that actually predate PDE theorems are just representations of a larger phenomena that is occurring from a different field, from something called PDEs. So that's one example. All right. Another brief thing about Laplacian that will make this estimate seem more reasonable. And that's the following. So look at this. So suppose we have a function. We have u from some domain, nice connected domain with the boundary omega into R, and u xy is equal to f of xy on the boundary. Okay, where f is some given particular thing, particular function. Okay, in fact, let's consider the class of such functions. So consider let's call it f of little f omega, the family of all such functions. Family. I don't know, it's about family. Family, something like this, right? Family of all such functions. Okay, good, thank you. And then let capital F of u be the integral of the gradient of u squared dx. And we want to minimize capital F, oh, I shouldn't use F twice, let's call that G. Or let's call it E. We want to minimize E over this function class, okay? And we want to E over capital F of omega. Okay, let's assume we can do this. Suppose we find the minimizer. Suppose U is the minimizer. And then let phi be this twice differentiable function with compact support contained within omega. So I write it like this. So that means that this guy is only non-zero on some set which is strictly inside omega. Okay? So in particular, f of xy equals 0 on the boundary of omega. Okay? And then let, say, w of t be the integral of omega of this thing plus t times this squared. I'm gonna write dx dy, I guess. Dx dy, just because I'm using this. Okay, now u is meant to be the minimizer, right? So u of t0, say that again, u of 0 should be the smallest value as we move around t. Yeah? Because as we move around t, we still satisfy the same boundary conditions. Because this thing is 0 on the boundary. Yeah? Do you see what I mean, people? Give me a thumbs up if that makes sense. Yeah? So now this is just a function of one variable. So expect that w prime to be equal to 0, because when t equals 0, that should be the minimizer. That should be at least a local minimizer of this thing, right? So expect this to be true. Yeah? But if we differentiate this thing, let's see what happens. Well, we can expand out w of t, and then we get this. Just expanding out this expression here, yeah? So we can differentiate this thing easily, yeah? Because this is constant, this thing is just this thing, and this thing is this thing. We just pull out, we just have a quadratic equation, right? We just have a quadratic equation. So w prime of t, when we differentiate it, this is a constant term, it's not relevant. This is the only thing that remains. This thing is just going to be 0, right? So this is the same as having this, that is equal to 0. So here's a little formula you can just check for yourself. If we take the divergence of u, if we take the divergence of gradient of u times phi, then that ends up being the Laplacian times phi plus gradient of u dot this thing. It's just a little calculation. You just take the partials on each one. Okay, maybe I just do it. So because what is this? Because divergence of the first coordinate functions ux phi, uy phi, and then we have uxx phi plus ux phi of x plus uyy phi plus uy phi of y, right? That is this calculation over here. Yeah? So then if we apply the divergence theorem, because this thing has got 0 boundary values, we have that the divergence of this thing, so the integral of the divergence of this guy is the integral around this of gradient u phi, the outward pointing unit normal, which is equal to 0, right? Just the divergence theorem. And this is also equal to the following thing. It's equal to the Laplacian of u of phi plus this expression, dx. And that's the expression we had over here, which is equal to 0. So this is the equation we get from the fact that the derivative of w at 0 is just equal to 0. And then up here, I've written the gradient of u times phi, and I take the divergence of this. The gradient of u is a vector field, right? It's consisting of u of x, u of y. So then if we multiply by phi, then we have this vector field u of x times phi, comma, u of y times phi. Yeah? And we take the divergence. Yeah, we're going to have two terms as we act on each one of these products. U double x phi plus u of x phi of x. Yeah? And then u double y phi plus u of y phi of y. Okay? And then that's exactly this formula, that the divergence of gradient of u times phi is equal to the Laplacian, because this thing here is the Laplacian, times phi. Yeah? And then gradient of u dot product gradient of phi, because this thing here is gradient of u times gradient of phi. Cool. All right. These are just calculations. If you can't follow as I talk and you take notes at the same time, which I wouldn't be able to, then just watch over this video. These are just very elementary calculations. You'll see, you'll agree with this. Okay, but the point is that this equation now reduces to, and then by this equality, okay, we have that this thing is equal to 0. So this thing, which is this thing, is minus this guy, which is equal to 0. So this thing and this thing imply that the integral of this times phi dx is equal to 0 for all phi, which are compactly supported and smooth inside of omega. Okay? Cool. Now, so we're making lots of assumptions here. If the Laplacian is just a continuous function, and whenever we integrate against another function, we get 0, the only way that's possible is if the Laplacian itself is equal to 0. So if it is continuous, this implies that Laplacian of u equals 0. Because imagine if that's not true. We just take some point where the Laplacian is, say, positive, could be negative, whatever, and just take a little phi, which is supported around a tiny, tiny little ball, yeah? Where this function is positive, but almost constant because it's continuous. Yeah? And then if we just test this guy, if we just take this little compactly supported function phi around this point. So this is a point where Laplacian of u of x0, y0 is, say, bigger than 0. Say it's over here. We put a little function which is just supported in a tiny neighborhood around it. Yeah? And our function is positive. Yeah? Then there's no way that this entire thing can be 0. Yeah? Unless that's actually not true, unless the whole thing is 0. Yeah? So if the Laplacian is actually continuous, then this being true for all test functions, for all functions phi, means that the Laplacian has to be 0. Okay? So what we've learned is that if u is a minimizer of this energy, then u has to satisfy Laplace's equation. That's what we've learned. Yeah? Okay, now let's go back and think about calculus. So when we do calculus, so I should have perhaps raised the board. When we do calculus, we learn a lot about minimizing stuff, right? So if we have G from, say, Rn to R, right? And suppose G has a local minimizer at some point, say, now I'm just going to say X for this vector. So suppose G has a local min at X, then we know that G prime of X is equal to 0, right? Very happy with that, I hope, right? That's just multivariable calculus, yeah? What we're doing here is an infinite dimensional version of this very simple thing, yeah? Because now our space Rn is replaced by an infinite dimensional space, the space of functions like this. So later, or perhaps now, you're learning about function spaces. This is an infinite dimensional space, yeah? And our G is this energy acting on this infinite dimensional space. Yeah? And if we assume it's a minimizer, even just a local minimizer, what this little calculation was just the equivalent of doing this. Yeah? And this equation here, yeah? This equation here has its analog with this. This is the analog of this. Okay? Okay. Cool. But if we take some explicit G, and we have this, then what is this? This is a vector equation, right? So it actually says that this vector is equal to 0. So implicit in this is n individual equations, assuming all the partials of this exist, right? Yeah. This thing is an infinite dimensional equation. Now, I slightly wish I hadn't gone into that direction because it means explaining more stuff and I'm taking you further aside. This is the exact analog of this, except this is a finite dimensional equation and this is an infinite dimensional equation. Okay? All right. So this is a little glimpse into the future if you study analysis, which I hope you all do. Why did I talk about this? Well, because it's another way that we get Laplace's equation out. Yeah? And it's another reason we expect Laplace's equation to smooth things out, because we're minimizing this energy, right? So let's go back to where we started. We have some domain like this. We're minimizing this energy where we fix some boundary values. Yeah? So maybe it's higher here and lower here, and we're trying to minimize the gradient squared. Yeah? Yeah? And it should seem reasonable to you that if we do find the minimizer, something that does it, then it's going to be the thing that's going to be as smooth as possible, right? It's going to flatten out as quickly and as smoothly as possible while still satisfying the boundary data, right? So imagine you have some kind of like ball, draw a ball on your table in front of you, and imagine the boundary values are higher at some point and lower at some other point, yeah? And then you're trying to minimize some kind of a surface which has those boundary values, but connects them through the center, through the area of the ball, yeah? Then it's going to smooth out things as quickly and as efficiently as possible, yeah? Yeah? So Laplacian is, by its very nature, something that smooths things out, that makes them as flat and smooth as you can possibly have, right? So by definition, we are minimizing. We're trying to do the very best we can. And the very best we can would be something really, really smooth, right? Yeah? Yeah? If there's any kind of additional perturbations, then that's not doing the minimizer's job. We can make it flatter. Yeah? Okay. All this stuff is not, strictly speaking, complex analysis. This is all background or connections. So this won't be in the prelims. I might ask you some simple question about background in the midterms, because I want you to pay attention to this. Just generally, as professional mathematicians going forward, I also want you to develop a certain breadth. So there's a lot of good stuff that comes from being interested in more than one area. So when you start your PhD and you get specialized in one thing, and this is a mistake I made when I was doing my PhD, you get very into it and you don't learn about anything else. That's a mistake, because taking interest in other areas will really help your research. It might not feel this, but it just really will. So this is important. This is what I do want you to understand this. I don't want you to do just like, oh, this is not really part of the course. And this isn't actually hard. This is, if you go through this, if you feel comfortable with your multivariable calculus, this will all make sense to you. It's just elementary things. And this gives a kind of hint how closely connected this subject is to other things. And that's true for many other subjects, that they are this spider web of connections throughout maths, between areas that you don't even expect will be particularly connected. And this is just some examples of this. We were talking about the heat equation. Now we're minimizing this thing. It seems a completely different game, right? But it ends up giving us the same equation. Yeah? And it's also the equation we get for the u and the v of a holomorphic function. Yeah? Cool. Final thing before I raise the board. In this is a formal explanation. I skipped over a lot of things that are needed to make this rigorous. It's not obvious that there exists a minimizer, okay, because the function class of things that are one-time differentiable isn't compact. It isn't complete, also not compact. Also not compact. So it's not clear that there is a minimizer. There needs to be a wider notion of function space to allow this to be true. If we do have the minimizer, it's not clear that it's going to actually be regular enough to do any of this stuff. There are theorems that allow you to prove this. But all of these technical things that I skipped over can be gotten around. You can actually do all these things. And this thing is part of a subject called calculus of variations, because this is a variation, right? So when we take this little perturbation here, we're varying something, and we're doing some calculus to extract out some equation, extract out some consequences for the minimizer. Yeah? So that is one of the areas I actually work in. So